There are other kinds of greenhouse gases other than carbon dioxide. One is methane, a hydrocarbon, and the other is nitrous oxide, a nitrous oxide. Those are both put into the atmosphere by processes, industrial processes. For methane, burial and decomposition in landfill. So just rotting garbage creates methane. Agriculture, you may heard of like cow farts, fossil fuel, burning fossil fuels, melting methane hydrates. Methane hydrates are locked in mostly tundra or maybe out in the deep ocean sediments, and these methanes can thaw out. And when they do, that methane is released into the atmosphere. Nitrous oxide is off gassing from the production of fertilizer, but also burning fossil fuels. Nitrous oxide has a long residence time. It can spend a lot of time in the atmosphere. All right, so what are the effects of this recent climate change? One of those is the heating of our ocean basins. So in this diagram, I won't go through all the nitty-gritty numbers, but what we see is that the oceans, the surface of our ocean basins, is warming up way faster than the land. It absorbs that heat. And with the warming of the ocean comes the expansion of the water, which is it adds to the problem of sea level rise. Ocean heating also is just not good for the organisms in the ocean that don't want to be hot. They're cold water species, so ocean heating is bad for our oceans and adds to sea level rise and not good for those organisms. We see the melting of the polar ice caps and the melting of alpine glaciers. Polar ice caps are like Greenland and Antarctica. Those are melting. Here on the bottom left is Greenland, and showing the melt extent in 2005. Look at that in that red area. So we used to have a lot more ice that went all the way down to the beaches of Greenland, and these days in Greenland, for the first time, they're able to go crops. I mean, it's mostly cold water crops like cabbage, but still they're growing crops. Here's Oregon's Mount Hood and a look at glaciers in 1985 and then again in 2002. We're losing the glaciers. If this water up to her armpits for Lady Liberty here, that's what 70 meters of sea level rise. So that would happen. That would be if all the ice melted. We don't really think that's going to happen anytime soon, but that is what it would look like. Global sea level rise is the rate is increasing. If we look at the graph at the top, observed sea level change here, it is sea level is rising centimeters a year, about 2. So here are some predictions. So 2020, we are right here. The cursor is here, 2020, and there are 3 different graphs there. They like to say, like, one of the graphs is, the top graph is if we don't change anything. If we keep burning fossil fuels and making concrete and creating deforested forest, that top curve is what could happen. If we were to stop now, maybe the bottom curve would happen. And if we kind of wait a little while before we stop burning so much fossil fuels at this rate, maybe the middle curve would happen. So they like to offer it, the scientists do, as here are your choices. Do you want this amount of sea level rise? Do you want this amount of sea level rise? Or do you want this amount of sea level rise? Another far off but effect that could happen with changing sea levels and melting glaciers is changes in the turnover of the ocean basins. This is called thermohaline circulation. It is the convection cell that moves water from the warm equator up to the poles, takes water from the poles back down to the equator. The conveyor belt is driven by density differences. Cold, salty water is dense and it sinks, and then warm, less saline water is going to rise. If we go up to Greenland and we start pumping in more and more water into the North Atlantic, then the conveyor belt is going to shut down. We're going to start seeing less salty water up there, so it will be less dense. So it's going to be less likely for the water to and slow down that movement of water in the North Atlantic to the cold, deep waters. So what would happen if that happened? Well, maybe you've seen the movie The Day After Tomorrow, where that area of the North Atlantic, instead of getting that warm input of water from the Gulf Stream, that would slow down and that area of the world would freeze over. So melting the ice in Greenland and the Arctic sends a large influx of fresh water into the ocean, equals less salt by dilution. Okay, here's that day after tomorrow. The conveyor would shut down completely, meaning Europe would receive no warm water. Central Europe would freeze due to global warming. Oh my gosh. So let's keep an eye on that. Keep an eye on the conveyor belt. Make sure thermohaline circulation doesn't shut down because of melting of the glaciers. Other problems, agriculture right now exists in semi-arid regions with hot climates and little rain, like the area around the Ogallala Aquifer or the area that is irrigated by the Grand Canyon or the Colorado River. All that is arid environments, and we depend on either river water from snowmelt or from really old groundwater. And if the climate changes and weather patterns change, we really have to start thinking about how that's going to affect agriculture. If sea level were to rise, 20% of the world's land area would be submerged if all of the glaciers melted. We don't really think that's going to happen, but we're starting to see pressure in cities like Boston and Miami and Washington, D.C. and New York City. These are all being affected on the East Coast by sea level rise. Other effects is changing precipitation and other local conditions. So floods, droughts, forest fires. Every time there's a forest fire now in the western United States, the story of climate change is brought up. And we must think about, like, do all these forest fires mean that the earth is warming and we're not getting so much rain? And is it going to get worse? We don't have all the data yet, right? We got to keep watching forest fires over lots of years to determine if it's because of climate change. Changing regional climate could alter forest, crop yields, and water supplies. We're already seeing that happen right now. The diseases are being spread and animals are on the move. Marine species are changing their habitat. Organisms like lobsters in the northeastern United States are moving into deeper waters and moving further north because of the heat that is being experienced off the coast of New England. Deserts may expand into existing rangelands. We're seeing that right now in the Sahel of Africa. Some of that is because of just climate patterns, but it's also related to overgrazing, and there's just not as much rain in the fringes of the desert, and so we're turning more and more rangeland into desert. Watch this video. I'm not going to click on it now, but you should watch this video. There once was an island, and maybe Google it and learn about how the South Pacific island nations, each of these areas that are circled by the dotted lines, are whole countries and nations and cultures. And as sea level rises, we start to have these environmental refugees where the people of these island nations have to move. And if you think about what that means, these island nations have their own cultures, they have their own languages, they have their own art, they have their own customs. And every time they have to move, they are dispersed. They no longer have, like, the old people staying with the families, staying with the younger people. And they start to lose their language and lose their culture that way. It's a really sad way for humans to lose a really important part of just the history of humans. Anyway, it's sad. All right, this graph shows, let me break it down for you. So each of the different colors and the letters associated with it, each of the different colors on here and the letters associated with it, like MBH, JBB, each of those is a author or a research group, and that individual research group or author has a way of reconstructing temperatures. So this goes from current temperature around the year 2000 back to the year 800. So over 1,000 years, over 1,000 years of data. And the proxy they're using is different. It may be coral chemistry, or maybe it's that dendrochronology, or maybe it is other isotopes from different sea creatures, or pollen, or just weather data. So some of this, well, they wouldn't go back that far, but either way, it's data from different sources. And what it's showing is that all of the data comes together in the recent. So that black line is measured data that's actually measured with a thermometer. And what this is showing is, from all these different proxies, is that temperature is rising, and these models all predict that temperature rise. Okay. What is anthropogenic? Oh no. Why is anthropogenic carbon dioxide so important? What is the input of CO2 doing to our temperatures? Well, there's three different graphs here. The first graph in A is natural. So the gray data here is just background. Sorry, I thought I turned that off. I did. Background non-human inputs to climate change. So maybe with volcanic eruptions, or with sunspot activity, or El Nino. Oh my gosh. Sorry about that. Can't get my phone to just turn off. Sorry. Okay, the gray is just nature. What is happening that is not people. Red on the graph is the observed temperature anomalies from zero. And B is anthropogenic forcing. So this is anthropogenic input, mostly burning of fossil fuels, and what its effect might be on climate change. And C is all forcing. So it's taking into account natural changes, like things like sunspots and volcanic activity, and it's adding in that human element. And when we add those together, it really does match the observed annual global mean surface temperature anomalies. Whew. All right, what can we do about this? What are we going to do? So let's look at the carbon system. We have to get rid of all this carbon dioxide. The natural system has CO2 goes into plants during photosynthesis. It goes into plants, and the plants become bigger and they make themselves. The plant is going to produce oxygen, but also it respires a little bit of that carbon dioxide. The rest of it is put into the ground. The soil carbon, that is basically plant matter that now is sequestered into the ground. As vegetation and organisms rot, that decomposition, remember, is going to release some greenhouse gases like methane, but also carbon dioxide. Humans over here, we're generating carbon dioxide from factories and our cars and burning wood over here. So these are all the inputs to the atmosphere, pretty much. Decomposition, human generated carbon, plant respiration. Okay. Over here on the other side is the ocean environment, where from the atmosphere and churning of waves and that interface between waves and the sea surface incorporates carbon dioxide into seawater. And the phytoplankton in the photic zone of the ocean are going to take in that carbon dioxide through photosynthesis. Some of that carbon dioxide then, because it's locked into the phytoplankton, is going to die and sink to the seafloor and becomes ocean sediment carbon. That's a good thing. Storing those dead phytoplanktons on the seafloor, some of that is going to, in that photic zone, still decompose. And that decomposition would release some carbon dioxide back into the atmosphere. Some of that ocean sediment carbon through upwelling, which is a good thing, bringing nutrients back to the surface waters, is going to bring up decomposing organic matter and bring it back up to the surface. So those are the processes that move carbon dioxide simply around the land and the sea. All right, so if we put this into numbers, over on the left is consumption of carbon dioxide. One of those is the photosynthesis, and the other is the air-sea exchange. So we're storing negative 214 gigatons. If we go over to the right, the natural causes here are natural producers of carbon dioxide, plant respiration, a little bit of the carbon dioxide goes back into the atmosphere, the decomposition and rotting, and then moving some of that carbon back into the atmosphere from the sea, right, from respiration. But then we add in this fossil fuel use and the deforestation. So we have a net addition of carbon to our atmosphere. It's that plus 4 gigatons right there. And that's what's getting us. That's what is the climate change part, is this plus 4 carbon to the atmosphere. All right, so here's a look. Let me deal with the dogs. So here we are with the reality. We have carbon dioxide increasing in parts per million in the atmosphere. This goes to 380, but we know we're at about 412 right now in 2020 going into 21 at 412 ppm. So really off the charts for the last 400,000 years before present for how much parts per million are in our atmosphere of carbon dioxide. We're moving. By the end of the century, maybe we would have 800 ppm, maybe more. What's going to happen? The CO2 input is too fast. It's just too fast for the Earth systems to respond gradually. So the Earth isn't gradually increasing in temperature. What is thought is going to happen is the change in temperature is going to be all of a sudden and catastrophic. So we look at the news and we hear about the loss of an ice shelf here or a calving glacier there. Those are the catastrophic moments in time that we're just kind of getting used to. We're like, oh yeah, that melted, or oh yeah, that fell off that glacier. But the reality is we really, really, really need to pay attention to these events, because one day it's going to happen. We're going to hear about it on the news like, oh yeah, half of Antarctica melted, and we're not going to think it's a big deal. But those are the catastrophic events that are going to be taking place. Even if we decrease our carbon dioxide input now, we are still playing catch up, because there's 411 parts per million in the atmosphere. If we stop burning fossil fuels today, that's not just going to disappear. So we feel like, as scientists, that we need to think about and really concentrate on and really research the active removal of carbon dioxide from the atmosphere. Here's the top 10 greenhouse gas emitters. So this is, I show this data from 1991, and this is published in 94, 95. If you look at data today, though, those numbers have changed. Let's go here. So here is 2008. And China has overtaken the United States over on the left side. See that? And you can go to this link here and find more data. And what you'll see as we get closer to 2020, China is still increasing with its CO2 emissions. Let's talk about why. One of the reasons why is it's a it is a developed country now, and there's more and more and more and more production of concrete. And the production of concrete uses limestone, which is CaCO3. When they make limestone, they release carbon dioxide into the atmosphere. Also, it looks like the number in the United States has dropped, but really, look around at all the stuff around you. Most of the things around your room, in your house, wherever you are, in your classroom, in your car, most of that stuff was made in China. So we haven't really reduced our footprint. We've just moved it to China, right? Because our stuff is made in Asia. So we can look at the emissions from China and say, oh, China, 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 but it's really our stuff they're making. Okay. If humanity wishes to preserve a planet similar to that on which civilization developed and to which life on Earth adapted, paleoclimate evidence and ongoing climate change suggest that CO2 will need to be reduced from its current 385 ppm to at most 350. That was a statement in 2008. Now we're at 2020 or 2021, and we are at 411 now and rising ppm. So we have already busted through that 350 ppm. What are we going to do? We need to decrease the rate of input, so conservation, and reduce the fossil fuel use. This is all about turning the lights off and driving a more efficient car and stop buying plastic crap. And focusing on renewable energy, focusing on solar and wind energy, and improving the efficiency of the energy resources we use today. So our infrastructure needs to be upgraded, and we need to improve the efficiency of our cars. Get one of those cars that is electric sometimes and runs on gas sometimes, that kind of thing. So really thinking about our personal input and change in our personal carbon footprint. Improving agriculture and sustainable forestry, so not cutting down so many trees. And this really is something we have to think about when we eat, right? So making choices that are sustainable for agriculture and making choices that are sustainable for forestry. You can buy paper these days that is sustainable. You can eat sustainably. So thinking about that with your dollars, right? Let your dollars make the choices. Active carbon sequestration, that is pulling carbon dioxide out of the atmosphere. And how are we going to do that? We can store it in a geologic reservoir. So pull carbon out of the atmosphere and pump it underground. Fertilize the phytoplankton, give them some extra iron, extra nitrogen, and make phytoplankton blooms in the ocean. And then when those die, they would fall to the seafloor. And then lastly, mineral carbonation. So take carbon dioxide, mix it with some ingredients to make CaCO3, so mix it with some calcium, and make calcite out of it. That would be a perfect way. The mineral carbonation right now it doesn't work that great, and we would need a lot of energy to do it. Storing it in a geologic reservoir is tough because that could be really dangerous. And how do you make sure it stays in place? And fertilizing phytoplankton is tricky because what negative effect is going to happen? Maybe something like eutrophication. What's a negative effect of too much phytoplankton in the ocean? And do we want to play with the chemistry of our ocean basins? So none of those are perfect. So hopefully we will find another place to sequester carbon. One of those is planting trees. And it's not enough just to plant trees. We also have to do that stuff at the top, decreasing the rate of input. When we look at data with who's bought into this, do you think human activity is a significant contributing factor in changing mean global temperatures? Yes, no, maybe, or I don't know. So the yes people are almost 100% of climatologists who study climate change. They are saying yes, they study this, they read about it every day, they collect data on it. They are 98% in agreement. The general public is still down at around 58%. That's not enough, because if we don't have the buy-in from people, then are they going to really try to, because doing this costs money and it's hard. It's harder to think about this than not think about it, right? Ignorance is bliss. But maybe we could be in bliss if we just care a little bit more. I don't know. So, yeah, it's good to learn about climate change and understand where that data comes from. If you understand where the data comes from, and then you will buy into a little bit more, like just say, yes, this is a thing. I understand climate change now. And then that translates usually to voting, and voting is a good thing.